we have this algorithm that is insertion sort, and we were working on it last time, and I realized literally this morning what was wrong with it. So we have this mute j thing, but really we want a 1 here, and then we can just make this I minus 1 because we start at 1, so we can subtract 1 from that. We could leave that in there if we wanted to, but it's really not a big deal. And this didn't work, and let me show you why. So if we cargo bench this thing, not bench, cargo test this thing, you'll see that it fails because it doesn't touch the first argument. And if you look really carefully here, we have this j greater than 0 thing, and that's because this thing is using 1 indexing. So because it's using 1 indexing, we never get to the first element because it's basically saying here the first element is a 1. So they're tying the 1 here, which means that this needs to be equal then. Interesting. It's useless. Comparison is useless due to type limits. What? What does this mean? Rust. Okay, so the compiler doesn't seem to recognize this error on anything other than literals. So it works with that. Okay, so we could say stood usize min. And it works? Oh, that's really weird. Okay, that's interesting. Okay, so this is a weird note. If we use a literal 0 here, we get comparison useless because of type limits. Oops. We can get around this by not using a literal. Okay, so then we go back to stood usize min, which is a constant, and so it is happier for some reason, which is pretty weird, but that's fine. And then we can just like go down and go from there. So I'm pretty sure that this will fix the bug. It does not. Why does it fail? It panics. It subtracts with overflow. Oh, because of this, because we try to subtract this from 0. So if j equals 0, 0, else j minus 1. Oh, no, but then that will just infinitely recurse, which is the problem. Programming like this is really annoying, actually. So what I think we should do is say Um, we need to move this stuff around. Or we can just break. Are you allowed to do that? Because we can't say like if it's greater than negative, or we can't like go negative here. So if j equals 0, break. Is that like allowed? I legit don't understand what's going on now. Okay. I guess we got to think about this because something goofy's going on that I don't understand. Hey, Bruts. Okay, so let's say I equals 1. Well, let's just start a table. So we'll have j key. And I guess we'll start there. So if I is 1, j is 0, and a of j is 4, I believe, in the test. Hey, CRLS. What is CRLS? And hey, Talus, probably not pronouncing that quite right. Yeah, so we're doing Introduction to Algorithms, and this book is very imperative. So like you can see over here that we're like looking at this pseudocode for this algorithm, and that's why like it looks this way. So we basically chose a non-functional language to go through the book because all of the examples, yes, I see. Yes, that's the right author list. So we chose a imperative language to go through this, but now I'm like already regretting doing this because there's like there's a index battle between 1 indexing and 0 indexing, and now I'm like I can't get the first one to sort, and I don't really understand why because like I'm using some imperative state thing, and now I need to understand how it works, which is like kind of annoying actually. So if we look at our example, a sub j is this input, and it's 4. So our input, I'll just put here, is 4, 5, 3, 2, 1. I mean, it definitely has something to do with imperative versus functional, because I would never write anything like this in Haskell, right? Like I would never write this code or code like this, right? I have like this internal mutable state that like I'm messing around with, and this is probably not how I would do this. Like I wouldn't write code like this in Haskell, would I? Like if I was doing insertion sort, how would I write this if I was doing a functional language? I would generate a new list every time, or generate sublists or something. Anyway, I don't know. I don't think I would write this code. There's an internal mutable state that I have to play with, and then I have like this 1 versus 0 indexing issue comparing these two things. I don't think it's not that. All right, I'm losing track of my thoughts here. So a sub I is 5. No, that's not right. I have this backwards already. No, I had it right. I would map over it. I would never do that, basically. All right. So we have these things, and then we're saying, like, if J is greater than or equal to the minimum use size, which should be 0 if I understand correctly, and A sub J is greater than the key, which it is not, so we'll move to the next one. That means, like, these two sub pieces are sorted. And then we say A J plus 1 is the key, which stays exactly the same, right? So we don't do anything on that line. All right, so number 2. So we 2, 1. And then A sub J is 3 and 5. So we need to certainly do something here. So J is obviously greater than or equal to this. And oh, is that backwards? No, it's not. Why does this look wrong? Right, like, don't I need to, like, shift these? Because 5 is high? Because this says, like, don't go into the list, right? Maybe I should write A sub I, A sub J. Also, this is backwards again. No, it's not. I've completely lost my ability to think about code like this, apparently. Like, why is this the... I don't know. I think I need to keep reading because I think I'm lost. So, questions are like... How do I do this? I think I just go like this. And then, is this thing really 0? That's a question I have. Okay, so curious about that. Yeah, I think we're going to talk about loop invariance and correctness and stuff here in a second. So, but it seems weird to me that I can't just, like, translate this code and it, like, works. It's kind of annoying, actually. Like, it feels to me like Rust using use sizes here is actually kind of screwing me. I suppose you could just say while j not equal to 0 here. But this is... Oh, this is probably not supposed to be break either. It's probably supposed to be continue. Well, no, it can't be continue. We need to break out of the while loop. Okay. All right, well, then let's just keep reading loop invariants, and then maybe this thing will be more clear. I find it kind of frustrating that that's the case, but I don't know. Okay, let's keep reading then and see where we get. So it says loop invariants and the correctness of insertion sort. This figure. So figure. Oh, what's figure 2 2? Okay, here we go. What are these blue arrows? So the okay. So swap. Okay, that's useful. The index I indicates the current card being inserted into the hand. At the beginning of each iteration of the for loop, which is indexed by I, the subarray, a contiguous portion of the array consisting of elements A1 to I minus 1, constitutes the currently sorted hand. And the remaining subarray, I plus 1 to N, corresponds to the pile of cards still on the table. It's talking about this in the terms of like sorting cards, if that's not clear, like a deck of cards. In fact, elements A1 through I minus 1 are elements originally in positions 1 through I minus 1, but now in sorted order. We state these properties of A1, A minus 1 formally as a loop invariant. Okay. So at the start of each iteration of the for loop, the subarray A1 to I minus 1 consists of the elements originally in A1 to I minus 1, but in sorted order. Loop invariants help us understand why an algorithm is correct. When you're using a loop invariant, you need to show three things. Okay. Initialization. It is true prior to the first iteration of the loop. So that's true in this case because the first subarray is always just like one thing, right? Yeah, somebody already brought that up, Talas, which is kind of funny. I don't remember who it was, but somebody did. Okay, so maintenance. It is true before an iteration of the loop. It remains true before the next iteration. Sorry, it's hard to write like this. So my handwriting is probably not super great. Because it's like it's not, the tablet's kind of just in my hand like this. And termination. So the loop terminates. So it terminates. the invariant. Yeah, I guess the invariant is true. Okay, so there we go. When the first two properties hold. Yep. Sorry, I'm trying to read through this. The loop invariant proof is a mathematical form of induction. We're not going to do that, probably. The third property is perhaps the most important one, termination. Since you're using the Okay, let's see how the properties hold for insertion sort. We start by showing that the loop invariant holds before the first loop iteration when I equals 2. The subarray consists of just one element, A sub high, which is in fact the original element in A. So actually, it might be useful to literally print out at the beginning of the loop. So this is going to be called well, actually, I guess that goes here, huh? So in the initialization in this jeez, I can't speak right now. I'm sorry. Initialization step, we want to print the subarray to I. So we're going to print the array, which is A, and we're going to print the array from 0 to I. I have no idea how to slice these things. Expected type. Rust. Slice array. Oh, dots. Thank you, Ice. Standard marker. Okay. Just use this maybe. Okay, so this thing needs something called sized. Okay. Yeah. 1.4. Okay, and then just go ahead. Do this too. Oh, maybe I don't need this because like maybe it's smart enough to figure this out if I just get rid of this. Where's this thing? Display Rust trait. Standard format. So standard format display. Okay. Now what? Okay, so it can't use this. It needs to use debug. Just use debug. It's also in standard format. Okay. Just please do the thing. Debug. And then there you go. Yeah, slicing is like me just using some term. It doesn't really come from Python. I just use that term. My terminology has never been strong. Okay, so there's our initialization step, I suppose, and that needs to remain true for each of these. So, yeah, that's fine. To me, they're the same thing. There's just a particular thing in a slice. Like a slice means something specific in Rust, but that's fine. Um, will I see the print output when I do this or no? Yes, I will. Okay. So it it isn't true. Yeah, I see. I understand that. I understand they're not the same thing, but I'm not part of the Rust community. I'm just a guy writing Rust randomly on the internet. So why is that? This 3 is not getting inserted into the right spot. Because this isn't J plus 1, it's J. Right? So this used to say greater than 0. Because when it was 0, that was our loop terminator. And this time our loop terminator is 0. So it should be A sub j equals key, I think. Yeah. There it is, I think. Almost. Um, oh, I can't do that there. Like, this doesn't work for the last one. Man. Um, why doesn't it work for the last one? Um, let's. Okay, so we have the initialization. So we start with 4. And then we just overwrite it immediately, which is why it doesn't work. Uh, okay, so because you exit the loop in 2 different ways. If you exit through the condition, you will have executed line 22. If you exit through the break, you don't. Yeah, but I can't execute line 22 if j is 0 because these things are use sizes, right? I can't go. I see what you're saying, though. I think I see what you're saying. I just don't know how to fix it. You should review the whole indexing system. What does that mean? Oh, probably. I think you're actually right there. Yeah, it does. Oh, let I go from 0 to len minus 1. Uh, but why would we want that? I mean, I guess we could do that, but I'm trying to write it similarly to this, but maybe that's like not a good idea. Nice. If I have to write it that way every time, that's going to be kind of annoying. But maybe that's the only way to do it. Yeah, but this doesn't work either. But I am like changing semantics at this point, I think. Maybe not. Oh, I wanted to look at this. This is in fact 0. It is. Okay. Let me just make everything 5. Which is actually kind of weird. From below. From below. I'm not sure I understand what from below means. I think I understand what maybe what from above means. Uh, you can't get index minus 1. Yeah. So that's kind of like why I need to start at 1, right? But you can have invalid index length. You should shift all by 1. You should shift all. You should shift all by 1. Don't understand. That's what I'm doing. As a person who cried on the Corman, I strongly suggest you use another language. Yeah, shift all by 1 kind of sounds like something someone would chant in a cult, actually. That's kind of funny. Shift all by 1. Shift all by 1. We could use a different language, but I feel like that doesn't fix the problem, does it? In this particular case? Like, I guess I don't even understand what the problem is. Mainly because I haven't thought about code like this in a long time. So what is a lang? Yeah, it's not a good call. For what it's worth. What is this thing? Is this thing uh the end, or do I need to shift that up? Yeah, probably. Um, I'm gonna do that here in a second for sure. I just want to I want to know what this is too. Is that what's the bounds real quick here? So it is 5 and this is 4. Okay, so that's fine. Yeah, I guess that's true. But so one of the things that was, um, okay, so there's two things that are important to me, and I guess you both of you would have missed this, which is fine, no big deal. Um, the two things that are important to me are static types and pattern matching. Those are the only two things that I care about whenever I'm picking a programming language. So the options were basically for me like Rust or Kotlin or Scala or something like that. Um, but I'm trying to learn some Rust along the way. Yeah, it's just like yeah, it isn't really getting in my way at the moment. What's getting in my way is me being dumb, basically, because I'm not a very smart person. Um, yeah. So okay, let's think about this again. Like let's just go line by line and think about indices real quick because I think I'm losing my mind. Yeah, Rust is hard and algorithms are hard. I agree with that. But I don't think that this is get smart then. Yeah, I don't think that this is necessarily that Rust is hard. It's just that like I have to figure out a good system for converting the indices back and forth. Um, and like that's what I need to be able to do. Otherwise, this is going to be very hard. And then hopefully, as I get more familiar, like my brain will be okay with these kinds of loops again. They're like just not okay with these loops right now. Um, that's a really good point. Uh, so okay, so if we go 1 to n, this needs to be 1. We're subtracting 1. So is n length, I guess. Because if that's the case, then this is supposed to be n minus 1. Let's see. At a certain point, you'll have to use pointers. That's fine. Book to Rust is -1, and Rust to book is +1. Yes. So if I understand correctly, we need to shift both of these things down by 1, right? Otherwise, this isn't going to work. Okay. Step 1. Step 2. Key is a sub I. This doesn't change. This is going to be the same. It's not going to be. No, it is. No, it's I. Okay. J. Chat's going very fast. So this stays exactly the same because it's not like we're just comparing I and J here. So I think that this stays exactly the same. This needs to get to 0, otherwise it won't work, right? Because it needs to be able to get to 1, and we need to be able to get to 0 in this case. So this has to be an equal sign. Otherwise, I'm not going to be able to do that. Although I guess we could just say J plus 1 is greater than U size, like this instead. So that we're kind of shifting. And this should all be the same. I think. Or do I don't think I have to shift this. I still think it's j plus 1 and this. Well, no, because if that's the case, then this would remain a j plus 1, right? And then it doesn't work. So I think I do have to shift all of these. This is incredibly annoying. So subtract 1. I don't know. I don't think I understand how to shift these indices. I really... Okay. So start printing stuff. Man, I am a dum-dum. Sweet. So JI is like the initial J, and then we'll print the J in here. And then we'll print A sub J. And really think we just want A sub J. Okay. Well, no, because wait, we want this to go to 0 basically. Oh, and then we do this. Yeah, you're right. So that's why we need the J equals 0 break thing. But I think that doesn't work because of this down here, which is like the biggest issue, is that like it's truly written to be in one indexing. I don't know why. Why is that the option? Yeah, this being a U size is kind of a problem. Well, it's not really a problem. Anyway, so we want A sub J, and we want A sub J. I haven't written code like this in 2 years, so probably gonna take me some time. I don't feel bad about it. We just need to think carefully, just practice. We'll figure it out. Okay, so here's the first loop. The key is 5. J sub I starts at 0, which makes sense. So we don't get in here because, I should do Okay. The key 5, 4 not greater than 5, so we don't do anything. This is really problematic because we shouldn't do. We need to change this, otherwise it's not going to work. Okay, so now we get here. So we are encountering basically this sorted subarray, which is the loop initialization. Wait, is this the maintenance one? This is the maintenance one. So the maintenance one is correct because I guess only the first one is. No, I think this is still initialization. We encounter the key 3, and our initial J is 5. Okay. So J is 1, A sub J. Oh, whoops. So we set AJ1 to AJ, which is 3. No, we set AJ plus 1 to A of J. Okay. And then at the end, we need to set A sub J equals to key, or you're not going to get the behavior back. But that doesn't... No, I'm lost. Completely lost. Okay. Delete all this code. Let's try it the other way. Let's not use that as an example and just like... can you try setting J to I in his initialization instead of I minus J? A sub I just gets set back to the same value instead of setting A sub I minus 1 to a new value. I feel like there's a J or a 1 mixed up here because I'm confused. Can you try setting J to 1? I see it. I see it. Here. Yep. Thank you. The line numbers help a lot because like I see your... It made sense once I figured this out. Okay, well anyway, we can just like see what it does. I think I've like gone way off the deep end, so things are gonna cause all kinds of problems. Oh well, actually, it did work. Kind of. I mean, like it didn't work. It's actually it's almost sorted the wrong way. Okay. Which is kind of funny. Why is it that way? Oh, it's just not doing anything, I think. Okay, so if we set that, we want to get rid of this, I think. I I don't want to look at this code anymore. Let's stop and let's just start from scratch because it's not helping me to think about it this way. All right. Um I do think we want to start at 1 because this is going to be like this. Okay. And then we want to switch them when what is true. So we're going to go to step back to the beginning and we want to know if in each case is the thing we're looking at if we look at this thing and it's greater than j, it's greater than the thing we care about, we just flip them? I think we just flip them. Okay, so the idea of the algorithm is to put an element in an outside variable and then replace it with a. Okay, replace it with a question mark, like a hole. Then you shift things around. Okay, so let's have a hole. So is this our hole? Is this the hole? If we find this thing, it's the hole. Index J. This picture is like kind of not helping me. First of all, let me do one thing. I have a picture in front of me. I need to just like figure out how to reference it better. I'm also going to put the actual example in here. 6, 1, 3, 6. Okay, so we start here. Key is 2. So we're going to, because AJ wait, AJ is 5, is greater than key. We have the whole, which gets 5. And then at the end, we stick our key into well, I guess the whole is like, well, it's 5. The whole is like the here. Let me draw it this way. So the whole is like here. There's 6, but whatever. And then we're gonna put the A sub j into whole, and then the key into a j minus 1. The whole has index j. Oh, I see. Okay, so we're going to put the key into the whole. Like that's what the whole becomes, and then the key goes into a sub j, and the a sub j into aj plus 1. Something like this. We create the whole in a sub j, which is 0 in this case. And then we move the current aj to j plus 1. And then we put the key into a sub j. I think this looks right. We'll have to do one example where the element before 5 Yep. Yeah, I think I have that written right. Yeah? Maybe this line is like kind of wonky, but I feel like I understand. Maybe. Okay. So let's try to do that. So we found the whole. So we need to fill it with a sub j. Or sorry. Did I have this right? I can't remember. Yeah. A sub j, the other way, the other way, the other way. Yep. So that becomes that. And then at the end, the key needs to go in A sub j. You may want do I? Oh, maybe that will this line is also really problematic, right? Because I think this is the problem that we saw before. If we run this now, I think that j minus 1 into element j. Why is it j minus 1? I don't understand the j minus 1 part. Because we want to move the key here and the 5 here, right? The whole is j. Yep. So if the whole is j, then the next one needs to take its place, right? That's what this is saying. This one is the key. J plus 1 becomes A sub j. So that this is 100% right. I feel like this is 100% right. Oh, we also have to decrement. But we need to look at it as a... Isn't that why what I just did here? I think I need to try the second iteration by hand. Although even the first iteration isn't working, so something's wrong here, and I don't know what. It's like there's some like okay, so in the first iteration, a plus j, a j plus 1 is 4. But no, it's not. It's not 4. Because okay, so in the first iteration, the key is 2. The key is equal to a sub j, j plus 1. Those are the same thing. It's not, j plus 1 is not 4. What's going on? Okay, so we're saying that's because you need j minus 1. I guess I don't see why I need j minus 1. J should be initialized with I. Okay, so let's do that. That's fine. Let's try this. So our key is, in that case, a sub j, and that's 2. Okay. So now j can never be 0, so you'll never shift out of 0. That's 100% right. So we need to be able to get to 0. And the only way we can do that is by casting the U size to the thing. I hate doing very much not having fun right now. Okay. Oh, that's why we need the j minus 1. That's what you're saying here, kind of. But it's a j minus 1. Sorry, I need to think about it. Okay, so key is a sub j is 2. We're thinking about j minus 1 here. I am not entertained. This is very hard, and like I apparently just need to like write some boring for loops with regular math because my brain hurts. Okay, so this is AJ. So now we're saying, is j minus 1 greater than this? If it is, we need to flip-flop them. So we have our whole, which is a sub j. So this is like the thing we're trying to mess with. We need to put a yeah. Well, the obvious maps are fine. It's when we do these like while loops in between where that's when I start to get really messed up. My brain doesn't think in while loops. The loop condition was fine before. What was the loop condition before? This? I guess it's fine. Yeah, it doesn't really matter if it's j minus 1. But anyway, if well, maybe it does matter. I'm not 100% sure yet. But we're going to create this hole. Then we're going to put j minus 1 into that. we'll just skip the first one, I guess, right? AJ minus 1 into that. And then at the end, we need to take AJ into AJ minus 1. No, this is AI. And this is into... No. I'm confused about this part again. K? Where's K come from? Oh, key. Key. Okay. Yeah. This is fine. Put AJ minus 1 into AJ. So we still don't flip the first one. So J should be equal to 0. No, it's not. Because it's 1. Line 14. I thought we said that this was right. Oh, yes. Because that needs to be a constant, because we're flipping stuff. I'm not convinced that this is doing the right thing. Like, is this doing a Python-y thing? The value you have... Yeah, I don't understand. I'm lost. So, okay. We go down. In this case, we J minus 1 to 0. I don't understand why. Oh, wait, no, I do understand why. Otherwise, we shouldn't flop. I It's so hard. This is why I wanted to do this, by the way, because... oh, that's not going to do anything. This is why I wanted to do this, because I thought this was going to be really tricky. And it is really tricky, and I'm having a very hard time with it. Not surprisingly. So it's good that we're doing this. Okay, so let's think carefully about this again. Okay, so we have a minus 1 is 5. So because aj minus 1 greater than key... Yeah, it was way more tricky than I was expecting. I thought it would be easier, but I'm way out of practice of just doing like loopy code like this. Create hole. this is the hole. Or is this the hole? What's the hole? God dang it. It's whatever the original. I think it's this. Right? Okay, so then let's do the next iteration on the tablet, I guess. RM view. Why? I think because it went to sleep, it was like unhappy. Ol has index J, so I had it in the right spot. This is so annoying. No, you can shout. You should shout at me at this point. I'm probably incredibly annoying to watch program. All right. Okay, so second loop is 2, 5, 4. It doesn't matter after that, right? Like, because we're here. So I is 2, J is 2. Oh, you can't see this. Jeez. I'm being a goofball. There you go. Well, I guess it doesn't matter. I mean, maybe we want the code over here. Okay, so we start. I is 2, J is 2. And then we're looking for the key, which is equal to 4. And then A J minus 1 is 5. So we hit the loop. So we need to create a hole. So that hole is basically 2. The hole is this one. Well, I think it's this. It ends up looking like that, I guess. Right? And then this for well, we move the 5 and then we go backwards until we find the thing. The hole has index J. It just it's I don't know what to put here because there's like what do I put here? I don't know what to put here. I mean, I guess like it has value 5, so it's still 5. And then we move this into and then Hey, Arid Swan. How's it going? Or a red swan. My bad. How's it going? Thanks for the follow. I have no idea what you're writing, Ice Clown. I always call you Ice Clown, and that I just realized that your name is not Ice Clown. This is called Introduction to Algorithms, and I'm basically punting really hard. What is FOU? Le Clown? Anyway. I do not understand. Okay, so it's like you move this 5 and then you find the anyway, you find the J where this thing goes. So this thing ends up being J at the end of the day. So you fill this with 4, right? That's basically what we're doing. So Hayes Anderson asks, how much previous experience with algorithms do you have? This much. A big fat 0. Usually the way I operated before was basically I found like whatever mathematical construct I needed, and I just like called somebody else's library. That's basically what I would do. Oh, this isn't J. So this is ends up being J equals 1. So we fill that with our key. Okay. I think I'm kind of getting it, but it's very slow. Does that make sense? So it's like we have 254. Yep. I've never touched algorithms in my life. I mean, I went through an entire theoretical chemistry PhD without learning about algorithms. You just call Matmule all the time, right? Like somebody else has already written Matmule. Somebody else has already written all the statistics like into the data science program. So you don't really need to think too carefully about how things are done. Just like call the library. You only need to think about the algorithm when it's slow, and like it's usually not too concerning. Yeah, my path has been really weird. It always has been that way. So anyway, it is what it is. So we move over here. We end up finding that we need to put the 4 at J equals 1. So we just do that, and that's why this last thing is here. So look, how do I say the last part? I guess I don't know how to say FOU in French. But anyway, I used to call you Ice Clown, so I'll try to be better about Le Clown. Yeah, I mean, I probably should have looked them up, but I didn't. Fu like kung fu, fu, Le Clown fu, fu, something like that. Okay. Punch clown, or maybe that's the clown punching me. Probably more accurate. All right, I think I'm following now. It's there's like this inner loop here that was really throwing me off. Moves the hole to the right instead of the left. Okay. Moves the hole right. I like that exercise. Moves the hole. So we're going to take the bigger number and put it into the correct spot. We actually also don't need this debug anymore, or I think this sized thing. Okay, so we need, if we're gonna move it, okay, and then let me start with the example again, because I want to like talk this out to myself. So now we are, I think that we start at I equals 0, j equals 0. And our loop condition is going to be like if we aren't at the end and a sub j plus 1 so we want to, okay, so we say this, we look at this 5 is our key. So key is AI is 5. AI is the key needs to be greater than a j plus 1 whole. Okay, so we start AI equals 5. The key is greater than this, so we need to move it to the right. So move j plus 1 into aj until the key is greater than, or well, is like not greater than, I'll just write that because I don't know what else to write, aj plus 1 insert key, I think. What? Yeah, I guess that's fair. Uh, it's pseudo whatever I'm writing anyway. What? Oh. There we go. Maybe I don't need this either. I just, because I had that for syntax wrong. So our key is still going to be AI. We need a mutable j, which is going to be initialized to I. I actually don't know if this will fully sort, but j, not, yeah. A len minus 1 key. What did I write? Key greater than j plus 1. Iterate j. And then it's still aj equals key, because we're basically just finding the place to stop. I can't type. Hello. And then we need to do something. I started in the wrong direction? Oh, do I have to start at the end and then work my way backwards? Otherwise, I guess it doesn't work. I was thinking that I was going to start from the beginning and then just start moving the bigger numbers over to the appropriate spot. But I guess that will never get the 1. Like, if I do that, I'll never get this 1 back to here, is the ID. I see. So this is going to be... okay. So we're going to go... Also, it says the outer loop invariant. Oh, I see. Okay. So like there's the like initialization thing, which is that a sub I end. I'm just gonna write end. Well, we can just write a lan is sorted. Right? That's like my check or maintenance condition or whatever. So this needs to go from... Can I do backwards loops like this? But it's not 0 to I, right? It's I to the end, right? Because my sorted loop is now moved to the end of the list, if I understand correctly. Yeah, because I have to go backwards, or I'm never going to end up with a sorted list. So, yep. Okay, I think we're on the same page now. Okay, so this is like the initialization slash maintenance condition, or that's what they call it in the book. And then obviously the termination condition is essentially the same as well. So we need to start from there. Okay, so if our key is a sub j, and this... So this is still the same, because we're going to walk backwards, and walking backwards... I don't understand. Dot dot equals line 29. Will this not work? Is this like a Rust thing that I need like an equal sign here to go down? Maybe this just doesn't do anything. It seems to work. Anyway, we'll see if the clown says anything here. Oh, okay, it's inclusive. I got it. Okay, okay. You're saying 0 is inclusive. Okay. So we have to go basically downward, or still to the beginning, so it's still downward. And what we want to know is our key, which will be 3, j minus 1, and if it is, we need to move a j minus 1. So we find j, which is our thing. We take 1, move it there, and then we go look for a case where this doesn't work, and then insert 3. So I think this is right. I'm just going to delete this now. What do we call this? Let's see. Doesn't look like it did anything. 524613. So something goofy's going on here. So our key is a sub I. So this is going to be 3. Oop, that's not how you do comments. Yep. Give me a second. Equals 5 is 3. 3 is greater than... I really can't think that the whole index is j. Like, it doesn't work for me. I don't know why. Okay, so this is 3. 3 is greater than 1. 1 needs to go into j. We subtract 1 from j, in other words, 4, although I think I'm actually not... This is 0, 1, 2, 3, 4, 5. Yeah, is 4, and we put the key 3. I don't understand. Okay, it's mainly for the meme at this point. The meme is good. It's working. Hang on. So we encounter 6. Okay. That's the key here. So we encounter 6, and the key is still greater than that. Is that the problem? No, I don't think it. I feel like it's this, but I don't know what goes here. I think it's just like I minus 1. Because you can't, you gotta stop or you're in trouble. Although it can't be I minus, if it was I minus 1, then this can't go here. So something goofy is going on with this. I think it's line 32 that's the problem. 15. Something goes here that I don't understand. Because I think this part's right. So I think it's right here that is the part I need to think about carefully. If I do, I can't do I minus 1 because we'll overflow. I also kind of feel like I can't start at I. I think I have to start at the 1. Fix line 34. Okay. Hey Brian, how's it going? I think I recognized your name before, but it's been a little while. Did you consider Skiena? I don't know what that means. I assume that's an author. Skiena algorithms. I did not consider this book, but I didn't. For what it's worth, I didn't really know that it exists. Oh, this might not be doing anything, right? Let's make sure it's actually doing what we think it's doing before I go too far, because this might not actually work. Because it didn't do anything. So I'm kind of wondering if it's literally just like not actually going down. Yeah, it's not. Like it doesn't do anything. So we need to change this. Yeah. I think because we're making a list, this has got to be is it just rev or is it reverse? Seems to work that way. Let me just comment that out for now. Just make sure we get. Do we want it to start at 4? It starts. I guess we do. Okay, so if I is 4, the key is actually 1. And then we want to know if we need to shift. Okay, I think I see why this wasn't working in my head before, maybe. We want to know, is the key greater than this? Right? Because j plus 1 is 3 now. So we're totally fine. And because aj equals I, we don't do anything. So our first loop doesn't do anything. Our second loop, I is 3. This is 6. 6 is greater than 1. So we're going to move to the right until we find this. We're moving to the right. We need to go upwards. Okay, so we're here. We've found key greater than this. We need to move. J is I. So we need to fill J with J plus 1. This one. And then continue doing that until we find the end. Yes, there it is. I got it. Hell yeah. Okay. I'm starting to see it. Like, the mechanics are starting to make sense. It was a little weird because this was definitely wrong, and that threw me off a ton. And then I wasn't really thinking about from the right correctly, and then we also had this reverse thing, which is really maybe a rusty thing. Like, it's not you can't really do reverse loops in Rust because we don't have like C style loops, right? Nice. So this is sick. This makes sense to me. Cool. Look at that. It was kind of painful for a while there. Holy cow, that was painful. But like I'm starting to see the mechanics. That's why you're saying that this is the whole is J, because it's like we're just shifting the whole. Let me do this. I think I also understand the shifty thing. So it's like, hang on, let me do no. Okay, so on that iteration, yeah, the whole is J makes sense now. So we're at J. We find that these things need to be swapped, so we create the whole. And like 6 is like basically in the ether at this point because we've captured it in the key, right? So then down here we're like, okay, well then just shift 1 down. The whole goes here. Okay, 6 still needs to get shifted. So 3 goes here, whole ends here, and then we like resurface the 6 there. That's how this works. And that's why J at the end ends up getting replaced with the key. Ah, there it is. Okay, I got it. Yeah, I get it. Nice. Okay, so let's do the same thing here just to. So this is like I equals what is this? 0 1 2 0 1 2 3 from the right example. Man, this is awesome. Okay, I didn't. The whole is J literally did not click with me until just now. So I appreciate for you for making that the meme because it was actually really nice. So let's move this one example forward. So if we end up with this and then 6 here, is that right? And then let's do I equals 0, 1, 2, 3, 4 from the left. Okay. So we find 4. Sorry, we pull the key out of 4 because this one's greater than it, and then we shift. And then still, we're not done yet because we have a 1. So we shift. Still not done. We shift. Still not done. We shift. Oh man. Okay. Um from the right sounds kind of weird, but I got it. Yeah, I feel really good about that actually. Much better. And then if we just look at like each individual case, our invariants hold, right? Because 2, 4, 5, 6 is sorted, 2, 4, 5 is sorted, 2, 4 is sorted, 2 is sorted. So every middle condition is held when we're doing the shift, and then at the end, since we terminate, wait, how does this work? It has to be these are all sorted actually, right? So I don't understand the middle condition. Is the middle condition that all of this has to be sorted? Okay. What's the maintenance condition is at the end. The maintenance condition it applies here. So maintenance condition applies here. It doesn't apply at any of these. Yeah. Okay. It doesn't apply at any of these middle ones. And if we look at I equals 4 and we just like look at these are all sorted, so our maintenance condition it holds. I think, if I understand it correctly. And I think they call it the maintenance condition because we haven't terminated yet. So this would be a maintenance one. And if we look at the beginning of the loop, then basically the initialization condition applies here. Everything before, like up to this, has to be true, or it has to be sorted. And then I guess the maintenance condition just becomes the initialization condition at the end of the day. Neat. I think I understand that. All right. Algorithms, look at us go. Okay. Um so the rest of this goes into like the pseudo example. Or sorry, it goes over the pseudocode, which I'm not going to cover because I think that the pseudocode is relatively obvious. Okay, so there's some exercises here that basically say like um use this thing as a model to illustrate the operation of insertion sort on an array. I think we were just doing that, so I feel like we're okay there. Like I don't think I need to do that again. And then there's now another procedure on the page. So this is kind of like similar ish to exercise 2.1-1 illustrating how insertion sort works. This is going to be exercise 2.1-2. So we need to bring up this. Let me draw the pseudocode here. Oh, I have like a ton of these open now. I don't know which one is the one I should have open. Is this one connected? It looks like it. I don't know why I opened a bunch of them. Okay, so we have this thing called sum array a n, and then we just have sum equals 0 for I equals 1 to n. Sum. I mean, this is like super easy, but a sub I return. Okay, so let's just quickly write that because it's super easy. So pub function sum array. So we need to have a t that's copyable. I think it needs to have, what's the other one? It doesn't need ORed in this case. I think it just needs copy. And then a is going to be, it doesn't need to be a mutable vector. It can just be a reference to a vector of t. Do I use vector up here? Nope, I just use slice, and it doesn't need to be mutable, but it'll be a reference. And then we're going to return this time an a, I guess. But it can't really be any a. I don't really know how you define like a generic integer. But they like clearly needs to be some kind of thing that can have a sum. So we're gonna have a mute sum equals 0. Oh yeah. We can just have. Is there a way to say like it's something that's addable? Like I know we don't have monoids, which is like a problem. If we had monoid, then we could just do this. But I think we should just pick a concrete t and be done with it. Let's just pick a concrete t because I don't think we have a monoid. So let's just do this because it'll be way easier. Well, really, we don't need to do this because we can just do that. And then we can say sum. Do we have plus equals? Probably. At I. Well, we can just say sum without the... Okay, this doesn't exist. We need to dereference, not pass it as a reference. We have the reference. We need to know what's inside the reference. So I think that this is like probably the closest representation to this if we wanted to pass a reference. I guess we don't have to pass a reference. And then you can just say this. No, you probably can't do that actually. Yeah. Are we sure we don't have plus equals? We do. Okay, I just had the types wrong. Is this, I feel like this is the most obvious representation of this function in Rust. Concretized to some t. Okay, anyway. So consider the procedure sum array on the facing page. It computes the sum of the n numbers in the array. State a loop invariant for this procedure and use its initialization, maintenance, and termination properties to show that the sum array procedure returns the sum of numbers in here. Okay. Yeah, I think if we wanted to do it like functionally, I'm guessing there's probably some way to just say like, there's probably like a fold. I just don't know what it is. So, um, oh, well, we have a mutable. Anyway, it's just called fold because that would be useful. Okay, and then ack. Do we just do this? Ack? We initialize a b. We have a function f. It doesn't really show us what f is, but anyway, I'm pretty sure I've seen this before. So we know x is just a thing, and apparently it returns the b, which is basically all you need is this b, and then you're good to go. I have no idea if which fold this is but implemented as. But I guess it probably wouldn't matter. In the where after the declaration. Oh, yeah. It's fold left. Okay. What? Oh, I see. So this thing has to be whatever this fn mute thing is, where b is the accumulator and the thing is the item, which I'm guessing is of type. This has something to do with the iterator type, I would guess. It's just like unclear because this is like a function from an iterator. So like where this item thing come from is not super obvious to me anyway. But yeah, it does look. I mean, this doesn't necessarily mean that it's fold left though, right? Like this could still fold from the right. and still have this signature, yeah? Or maybe I'm misunderstanding what you're telling me. Anyway, that would be like the functional version, I suppose. Okay, sorry. So what we're trying to do is um we need to know what the loop invariant is, and then it says oh yeah, I see what you're saying. Okay. Yep, I understand. So initialization, maintenance. Okay, so this is basically what it's asking us. State a loop invariant for this procedure and use its initialization, maintenance, and termination properties to show that the sum array procedure returns the sum of numbers. Um, State a loop invariant. There, there isn't one. State the loop invariant. Let me read more about this thing again because to me it doesn't look like there is one. Okay, so it says at the start, so for the previous one, at the start of each iteration of the for loop, the subarray consists of elements originally in blah, but in sorted order. Yeah, like I don't really understand what what invariant you're trying to preserve here. Like it doesn't matter. It's like the previous ones are already okay. Well, let's try it that way, I guess. Is this right? Yeah, we're not including the last one because it's exclusive. Okay. That's what I thought, but I wanted to make sure. That's why like this is just so much nicer. You don't even have to think about it. But anyway, okay, so if we're thinking about a loop invariant, what do we know at any given time? We know that like a sub 0 to I Is that the loop invariant? I feel like that's the loop invariant, but it feels like way too trivial. But maybe that was like the point. Um, so if we take the initialization, then we're taking the sum array of an empty list, which is equivalent to 0. Check. I'm not going to look up the maintenance condition, but the termination condition is that I think I did 1, 2, 3 or whatever is equivalent to 6, which is check. See. I don't really want to check the maintenance condition, but I guess I could do that if I really wanted to. Yeah, it's just like you basically just have to do. You have to look at every sub iteration and then ensure that the thing is correct. Could test this, but trivial, basically. Oh, I guess we could just add a check here as well, like a maintenance check or something. Okay. It's not about using an example. Oh, it's a math. Okay, that's a fair point. I don't know how I would prove that mathematically, but I feel like it's true. All right, so it says rewrite the insertion sort procedure to sort into monotonically decreasing instead of increasing order. Okay. So let's go grab this little one. And we're going to insertion sort decreasing. And I would hope all you have to do is flip this. But I need to think about it. Well, I don't want that one. I want this one. And then we'll say it's probably not that simple, but one can hope. It is that simple. Nice. Okay, so let's just think about an example because that has been helpful. So if we have like 5, 4, 3, 6 you tell us 1 or whatever, and we have I equals to 0, 3. Our key is 6. Our hole is J. We shift our hole. We shift our hole. We shift our hole. We drop our key. Check. Easy peasy. So you could take like an ordering function, and as long as you could produce like a Boolean here, you could easily write an insertion sort for some comparison function. I guess you're not guaranteed that all comparison functions terminate, though, for this insertion sort. They have to be like, it has to be a monotonically ordering function, I suppose. You could say that it has to be a pre-order, I think. Okay. This looks really big. This next problem. Okay, so it says, consider the searching problem. A sequence of n numbers stored in an array and a value x. An index I such that x equals a sub I, or the special value nil if x does not appear in A. Write pseudocode for linear search, which scans through the array from beginning to end looking for x. Using a loop invariant, prove that your algorithm is correct. Make sure that the loop invariant fulfills the 3 necessary properties. Okay, so pub function linear search. We can take a t. T needs to be equatable. And then we're going to take like an x, which is a t, and an a that is a reference to list of t. And we're going to return an option usize. Right? So for now, we'll just return none at the end of this thing, and then we can go from there. So let's write it in the I style. Okay, right. If x is equal to AI, you return sum. I guess you could just write, I think you could just write sum x. You can't write that. We need to return. Are we sure we need to return? We do. Because we need to break, basically. We want to short circuit. And if we never find the thing... Has it really been 4 spaces this whole time? If we never find the thing, then we just return none, call it a day, right? So I guess this is at worst O of n. Technically, we haven't talked about O of n yet, but that's fine. All right, so let's write 2 tests. I'm trying to write more tests. What do we call this? Linear search? So linear search works with result. I don't know. We don't need a mutable vector. We can just get the linear search for 1 in input passed by reference is sum 1 if we try to search for 10, we should get none. This is a test. We have to annotate it as such. And then things should still failed. Oh, it's the index. So yeah. So we have to find the index where 1 is. So that's 4. Whoops. Then we should be okay. Yeah. So that's basically the two functions. This one's very trivial. Like these problems are going to be pretty trivial. So so our loop invariant is that a 0 to I linear search x a 0 to I is none. Right? So if we give it an empty list and we search for x, we get none. If we give it yeah, I think that's right. Anyone have any issues with that? I feel like that's correct. I think that's right. Okay. So this next one's kind of. Oh, I should put. This is exercise. 2.1-4. And did I put the exercise number here? Exercise 2.1-3. Sick. Okay. So now we have exercise 2.1-5. And this one seems like a doozy. So we may want to write this down. So it says, consider the problem of adding two n-bit binary numbers a and b stored in two n-element arrays. A goes from 0 to n minus 1, and b goes from 0 to n minus 1, where each element is 0 or 1. Okay? So, okay, I definitely need to write this. Because we have like a summation. So we have basically a t, which is 0 or 1. That's our type. We have two arrays of the same length. A is a dot len is basically no, I don't really want to write that. Let's just write a dot len equals a dot b dot len. Come on, hello. It wouldn't erase. I don't. Sometimes it does that. I don't know if the screen is like getting scratched up from the erasing. Not completely sure. But sometimes the eraser doesn't play very nice, and I'm not sure if what that is. Maybe I should email them about that. Okay. So A is the sum I equals 0 to n minus 1 a sub I times 2 to the ith power. B is equal to sum I equals 0 n minus 1 b sub I times 2 to the ith power. C equals A plus B should be stored in the binary form in an n plus 1 element array. So okay, where C is the same thing. Okay, so write a procedure, add binary integers that takes as inputs arrays A and B along with the length n and returns array C holding the sum. What do I put into the last element of C? I don't understand. 0? I've never done binary stuff. So like, is there some kind of thing where they spill over? What do we call it? Add binary integers. So we're going to have an A that's going to be basically a vec of some t, which we'll define here in a second. But I'm just getting the B is also going to be vector of t. And we're going to have an n that's a U size. And what is this thing going to return? It's going to return an option of vec of this T type, which we're going to create here in a second. And for now, it's going to return none. And it's also going to return none if a dot len minus oh. Okay. So I think like this is kind of the scaffolding-ish. Except we got to remove this none here. But this is like one of the things it says. And I don't fully understand why yet. Has anyone ever done a problem like this? Okay. So we need, whoops. We're going to build a vector C. Is that how you do this? Okay, well, we also need one of these. So we need an enumeration. Okay, then we can remove all of these t's because they're going to be vectors of 0 or 1. This is going to be a vector of 0 or 1. And then we need to initialize an empty vector somehow. So rust vector initialization. Initialization. And then, so we need to get stand vec, and then we can use vec new like this. What is this complaining about? Private type is, oh, okay. So it's like, it doesn't want me to, it doesn't want me to leak this inner type. Like if I had this enum type and I didn't want to share it for whatever reason, that's why it's complaining, I guess. So add bit. Oh, nice. Good call. With capacity. Capacity. And then basically that allows me to like just push onto this thing and it's going to be like totally fine because the capacity is the right size. Okay, that's useful because I know the size in this particular case. All right, I have no idea how to do binary stuff. I have never ever learned. Like the only part I don't know is what you do when you add 1 and 1. Like does it give you a 0 and then a 1 on the next one or something? Add bits. Example. So, okay, so we're going to have a carry and a result or something. So if we do this, you're going to have a public struct add 0 or 1. And it's going to have a carry, which is a 0 or 1. And it's going to have, I have no idea how to write this. It's going to have a, like a result, 0 or 1, I guess. Hey, Viking. How's it going? We are working through this book. So since I'll just quickly go full screen here, we are working through Introduction to Algorithms, the 4th edition by these authors, Corman, Leiserson, Rivest, and Stein. And it's been very hard, but today we learned how insertion sort works, and I actually feel pretty confident about it, thanks to Tail-ass. The meme that came out of it today is, where's the meme? Here's the meme. The whole, no, the whole is index J. The whole is index J. But now I feel like, oh, I'm supposed to go back to this. I feel pretty comfortable about this. Now I'm like just messing around. I mean, I'm not really messing around, I guess, but I'm trying to add binary numbers, and we're basically learning how to do that in a if we were to represent binary numbers as a vector of a certain size. So I just learned that we need n to be at least one element larger so that we can bring over this carry value. And basically, we're going to match X and Y here, and we're going to say like 0 or 1, 0, 0 or 1, 0 goes to the add 0 or 1. I don't know how you initialize these things. This code is going to be really annoying for other people to read, but this is kind of how I would write it in Haskell, I guess. This can't be 0 like that. It has to be 0, 0. And then carry is 0, 1, 0. You're 100% right. It probably should come first. Yeah, I'm kind of just doing it by hand because it's asking me to do it by hand, I guess. So I don't really need to, but it's kind of interesting anyway. Okay, so actually, really, this doesn't need to take a 0 or 1. What it needs to take is a add 0 or 1, right? And then it's going to return. It's a folding function, essentially. Yeah, just practice. It's not particularly interesting, I guess, but there's got to be like a way easier way to write this, right? I don't know. I guess I chose to do enums, so that's my fault, huh? So I don't know how to pattern match out structures. Match struct. I would like to learn, so that's kind of why I'm doing this. So I guess it's just you. I have no idea how to do this bit. Oh, okay. So we can say, hang on. I would like to learn how to do this. So carry. Do we say equals here? I don't know. Result. This. Is this allowed? No. Okay. So that's how you construct these things. And then, so we need to pull out the carry and the other piece. So we're going to say add 0 or 1. Okay. And I'm guessing that these are like the things I expect them to be. Yeah? And then we can say match, carry, result, y. And then start dealing with the cases. So if we get, is there also a way to like use this so I don't have to type this all the time? Can I say use 0 or 1? Nice. That way I don't have to, because like clearly I'm using that syntax, so I don't really want to type it all the time. So if we get a 0, I guess we need to 0. It doesn't matter, and another 0, then the result is just carry 0 result. Is that right? Except we need to remove this now. And this is a like funny equals sign. Oops. Okay, so we needed to derive copy basically. Rust derive copy trait. How do I do that? Okay, we just say on the struct derive copy. Derive copy. I had to write this one a lot today. Why not? Okay. So yeah, we just need a mechanism to copy the thing. So like if we had 0 and 0, then we just need to end up with just with x basically. If we have a 1, well, if this is still 1, then it's the same thing, right? Because because if this is 1, then this is 0. Okay, so question is there a reason you called the enum 0 or 1 instead of bit? No, yeah, that was just in my head. But we could easily call it bit. Bit add. Yeah, I think so. Okay, so if we have 1, 0, 0, that's still x. If we have 1, oh, actually, if we have 1, it's the same thing, right? Because if it's 1 or 0, then your carry stays exactly the same. The only time it matters is when this is 1. What happens if they're all 1? Is that possible? Seems like it is. I'm just going to enumerate all of these because okay, so this is 1. This is still 1. Okay, like that. So we can have this, this, let's do it in the same order. Okay, this is the only part I don't know. The 111 case. Because the rest of these are pretty obvious. This is carry 0. This is carry 0. This is carry 1, 1. So what goes here? What happens when it's 1, 1, 1? I don't know. The answer's not here. So like maybe this is just like a bad representation of bits. Because if I delete this, it will say they're non-exhaustive, right? Or will it not? Oh, I guess that's right. Wait, but how? Does that make sense? I don't know. Does that make sense? I guess that's the only time you carry one. Well, what about this one? So both of these are the same? Result? Or am I missing something? This is like the only thing you can do? Line 129 is wrong? Is the carry supposed to be 0 here? Okay, so 0, 0, carry is 0, 0, 0 is 0, 0. Okay, the only time if they're 1 is when all of them are 1. I also don't understand this thing. I don't understand the notation on the right because I'm not like familiar with this stuff. No result is 0 there. Here? Yeah, like I don't know this math well enough. This is like one of those things where like you do need a ton of experience to like understand this stuff because okay, so the notation on the right is just binary. The subscript 2 only indicates the binariness of the numerals. Okay, so you could get a two digit binary number. But doesn't really mean anything to me, I guess. Is there like a better example here? There's always 0 on line 129. Okay. I'm not sure I understand that, but yeah, I this is like yet another thing where I need to. It's like one of my weak spots. I've never done binary anything, so I have no freaking clue how to do this stuff. Okay, so if the carry is 0, I mean, I guess that one wasn't so bad. Maybe I should just use an existing bit thing because this is not something I'm familiar with and be done with it. So bit. Is this a thing in Rust? I have not tried anything with bits or bytes before. So nope, this doesn't really mean anything to me. Nope, 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 nope. Um, this table is very confusing. Could somebody just give me a table? I don't really want to think about this right now. I'm like hungry and tired now. All right. So 0, 0, 0 is 0, 0. 0, 0, 1. You gave me a table. Is 0, 1. Okay. 0. Wait, what's your order? Is your order the same as mine? Okay. 0, 1, 0, 0, 1. Got it. Uh 1, 0, 0, 0, 1. 1, 0, 1 is 1, 0. 1, 1, 0 is 1, 0. 1, 1. Put this up here. And put that there. 0, 1, 1 is 1, 0. Okay. And then 1, 1, 1 is 1, 1. I think I got it. All right. So now we just start changing this business to vaca bits, bit, bit, bit. Okay. So 0 in 0. I in 0 n c dot what is it? Push? I think it's just push. Actually, we can't really do that. We need to do let bit add carry result equals okay. So we we have to get like the initial one, and then we can say if I equals 0, we'll have the right things, I suppose. So we're gonna have a bit add, and actually we do need to modify this, don't we? I suppose we could fold and zip, but I don't really want to do that. Okay. So this thing is gonna, it's not really an ACK, it's kind of like just a temp. And then this is gonna be B I. Oh, I guess it's doesn't matter if it's 0 or whatever, because you're already gonna have this thing. So it could just be temp equals add 0, 1, temp. No, that doesn't work. Okay, I'm too tired to finish this. I'm just gonna be honest with myself. Um, the basic idea is, I need to eat something. Need to determine the carry I need to finish this. I can do it. Maybe. Well, no, we can just say the first carry is 0 and then change it. So it's like, um, bit add carry So we need to create a bit add with the carry. And then sub I and the B sub I. Okay. Then we need to store the result. And we need to set the old carry to that carry. So this is called result. Push. Add. Oh, I think we can just say result I equals result. Okay, and then finally we say blah, blah, blah. We're gonna have the mutable carry. So that goes in the last spot. So ret a n is carry. Return ret. Well, I think something like this. Yeah, I think on 146, I think this one's right. So we basically start with a carry of 0, add the two things, and then take the result, and then we're basically just passing the carry forward until we hit the last case, which I think is supposed to be n. But if this is the case, then I think it's just a.len and not +1. Otherwise, I think you need to reverse. Reverse? I don't understand. Why would I need to reverse ret? Isn't that what I'm supposed to do? Or is that not how this works? Am I supposed to start from the end and work this way? I think I'm just doing it backwards because I don't know what I'm doing. Yeah. Wait. Yeah. Okay. Yeah. I think I understand. But basically, I just need to do this in reverse. And then you're saying that it's really this one. Like this? I think. Okay, that's fair. We can check this next time. So what is this thing? So this is exercise. Oh wait, I wrote this already. I times 1 times 1. So my reasoning here is that we're starting from the right, where we need to put our A's and B's are n-1 length. And then we're basically storing the results of the literal result is a dumb name, but result in basically ret of 1 to n, and then the carry goes in the first position. I don't understand binary addition, so this could be 100% wrong, but we can easily just test this and make sure it's correct. Does that kind of make sense? I don't know if this is the right thing, but that's what I'm doing. Whether it's right or not is a whole different story. I do like this pattern match let statement here. Pretty nice. So we need to test this. And we also need to come up with a better name here. I guess test this is fine. But that's basically what we need to do for next time. And then we'll start talking about analyzing algorithms, and we'll see there's like some interesting math going on over here. Some wild looking math over here, which will be fun. Then there's some more exercises, and then we talk about divide and conquer, merge sort, etc., etc. So this is going to be a pretty heavy chapter, but I think once we get past here, we're going to start looking at more like examples, and we'll hopefully keep nailing down like how these things work, because that's the practice I need to get.